Who happens to be my student in my quantum mechanics class a while ago, in my undergraduate quantum mechanics class. So it's really fun to be talking about how to improve student learning of quantum mechanics as a scholarly work. So basically, I do research in how to do this. And you can see that this has a lot of implications for workforce development, because quantum mechanics is something that is really important for a lot of different kinds of STEM jobs. And there are a lot of students who actually struggle to learn quantum mechanics. And what we have found is that even those students, even their understanding improves significantly after they use research-based learning tools. So basically, let me start by just saying that everybody knows that quantum mechanics explains microscopic phenomena. But the point is that developing intuition about quantum mechanics is very difficult, right? And it's also true that sometimes we hear about these collective macroscopic phenomena such as superconductivity or superfluidity. But even then, it's very hard to know why do those things happen. What's going on at the microscopic level that gives rise to these kinds of phenomena. So thinking in a scholarly way about how to get students to actually learn these issues well is something that we do. My group actually does. The great thing about quantum mechanics is that it has never really failed to explain what happens at the microscopic level. And experiments have always been consistent with this theoretical framework. Quantum mechanics is really a theoretical framework. And the point is that there hasn't been any experiment at the microscopic level that has actually not been explained by quantum theory. Now, so technological revolution has been possible because of our understanding of quantum mechanics. So let me just give you an example. And in fact, there have been a lot of talks already on this issue. So about what kinds of quantum mechanical systems we want to talk about, we want to help students understand. It turns out that Schrödinger equation is the most fundamental equation of quantum mechanics. And basically, Schrödinger equation talks about wave functions. So the interesting thing is that in quantum mechanics, wave function is central to understanding how things work, as opposed to you won't know the position of the particle or the momentum of the particle or the energy of the particle. Those kinds of things could in general be not well defined in a given quantum state, but somehow based upon the wave function, you might know that your system has maybe a superposition of different energies or different positions or different momentum. And now you have to think about, okay, so if I measure something, say energy of the particle, of an electron, what are the different probabilities of measuring different values of energy, for example? Or for example, for that matter, position. And thinking about these issues is quite difficult for students. Here I have actually drawn for you a problem that students often do, which is called a square well problem. But you can, as an experimentalist, make a square well by putting two different kinds of material together, one after the other, layering them together. And what I'm showing you here are the wave functions. For example, this is the stationary state, ground state wave function. This is the first excited state wave function. And you can see that these wave functions are delocalized in the sense that, like if the electron had this wave function, it might have a fixed energy, but it won't have a fixed position, right? And those are ideas that are really difficult for students to learn, because generally when we think about things, we think about, this is my position, this is my energy, this is my momentum. So the idea that different observables, things that you could measure, are not well defined is a very strange idea. We have also heard a lot about tunneling through barriers. Susan was talking about how she actually makes use of this, for example, in response to your question. But the point is that, again, since quantum mechanics, we are talking about waves and particles and the duality of those things. Sometimes the position of the particle can be well defined, in which case it could behave as a particle, but in other cases it could be very delocalized, in which case it could behave as a wave, and you can actually have this kind of tunneling through the barriers, which may seem strange, but all of these ideas are really important in actually applying quantum mechanics to diverse situations and be able to actually participate in this technological revolution. So the question, and then this issue of quantum measurement. So the point is, you probably have already heard about cats being alive and dead at the same time. So being Of course, cats cannot be alive and dead at the same time, so that's an exaggeration, but it's true that electrons can be in different states at the same time, atoms can be in different states at the same time, and only when you do the measurement do you actually collapse the system into a state in which whatever you are measuring has a fixed value. So these ideas, which are extremely important for making technological revolution and understanding the science behind those issues, are things that students are struggling with. And my goal, the goal of my research group is to actually help students learn these ideas. So another principle that students have a lot of difficulty with is this uncertainty principle, right? The more you localize the particle, the more its momentum becomes ill-defined, right? I mean, and this is an idea that is very difficult, again, for students to understand, but we have to think in a very careful manner about how can we get students to think about these things in a coherent way so that they can actually learn to apply these principles that actually have real implications for being able to push the envelope, right, in science and technology. So think about this particular experiment. The double slit experiment is, one of the experiments. This is done with electrons here. So the double slit experiment with electrons was voted as the most beautiful experiment by the readers of New York Times, right? In this experiment, you're sending one electron at a time through two slits. What are you seeing on the screen? You are seeing an interference pattern. You're seeing that there are some regions which are bright and dark, and bright and dark, like here you can see that this is bright, and then here it's dark, bright here, dark here, etc. And this is not what you expect if you're sending one electron at a time. Is the same electron going through both slits? And the answer is yes, because unless the electron itself, one electron behaves as a wave and goes through both slits at the same time, you're not going to be able to see this kind of a behavior. So it's a very counterintuitive behavior, and it's showing that electron is behaving as a wave. But the interesting, as it's passing through the two slits here, but the interesting thing is that when the electron arrives on the screen, what you see is just one dot, as though somehow it's behaving as a particle once it has interacted with the screen and it's become very localized. This is what I was telling you. Somehow the measurement with the atoms, this interaction with the atoms in the screen localized the position of the electron and made its position well defined. And now it's behaving more like a particle as opposed to this delocalized wave that went through both slits. So you can see how counterintuitive these ideas are, but we have to really get students to think about these things in a consistent, coherent manner in order to improve their understanding. Now, what I want to say is that unlike all of the other topics, quantum mechanics is particularly difficult because, as I said, now if you think about why is it that learning physics in general turns out to be difficult for students, when you think about it, a lot of ideas that you learn in physics and of course physics is about how the world works, those things are not consistent with your everyday notions. So for example, people think that an object, even if it's moving at a constant velocity, it must have a net force acting on it, and that is not true. Constant velocity means that there is no net force on the object. What people think that just because initially they had to give a push to get something moving, somehow that force must be carrying off with the thing, and that is why there are all these different kinds of misconceptions that people develop, and it becomes really difficult to teach even classical mechanics. Now, quantum mechanics becomes challenging because the kinds of things that you learn about, in classical mechanics course about Newton's laws and all, this time what you are learning is no, actually those things are just approximations, and what quantum mechanics says is that really the position, momentum, energy are not well defined. These are just operators that correspond to observables, and basically the wave function is something in a Hilbert space where no one can hear you scream. So I guess these ideas become so difficult that students, start, really struggling with these ideas. So our goal is to really have students think about these issues in a systematic way. And so we are really thinking about how can we help students learn quantum mechanics via development of learning tools that are based upon the findings of cognitive science and physics education research. So cognitive science, one of the things that we learn from cognitive science is that we have to actually build on what students already know. So if students have certain difficulties, if they have certain ideas, We have to take advantage of all of the things that they already know, but at the same time worry about all the misconceptions that they might have, and we have to bring out those things explicitly to help them actually think about, re-evaluating things so that they can organize and extend their knowledge and repair the things in their knowledge structure that might be faulty. And so what we are doing, one of the things that we are doing is developing these quantum interactive learning tutorials. And these things are based on the findings of the common difficulties that students have. And they use a guided inquiry-based approach to learning, where students actually, we start with what students already know, and then we build on their knowledge. And all of their difficulties are explicitly pointed out. Now the point is they often use these computer-based visualization tools, and they keep students actively engaged in the learning process. Now, for example, one thing that students have a lot of difficulty with is time development of wave function. So students have difficulty learning, they're thinking about what happens in those quantum states, in terms of the evolution of that state, in which the energy is well-defined, and the states in which energy is not well-defined. And it turns out that their state evolution happens in a manner in which the probability of finding the electron changes with time in one case and not in another case. Now students often think, oh no, it's going to be the same for all cases. What the quantum interactive tutorial might do, after students have predicted what should happen in the two situations, is that it will ask them to look at some simulation and work through it to see what happens in the two cases. So for example, in the case in which the energy is not well defined, what students might find is that, oh, these are time-lapse pictures. What they will see is that the probability density for finding the electron actually is changing with time, something that is not consistent with what they had predicted in those situations. And then what the QuILT will do, this quantum interactive tutorial will do, is provide them with guidance and support to help them think about why is it that things that the quantum states in which the energy is well defined are special when it comes to time evolution of the system compared to the ones in which the energy is not well defined. And then students actually are guided to build a more coherent understanding of these ideas. Here you can see we have developed many different tutorials on many different topics, including this double slit experiment or Mach-Zehnder interferometer, which is also a very interesting and counterintuitive experiment that really helps students think about these issues in concrete context. Also things like quantum key distribution, which is something that is that helps students think about how to use how to think about quantum information science and technology using an example in which there is a company that is actually making these quantum key distribution devices that helps you figure out if you're trying to make a common key with somebody, whether there is somebody who's eavesdropping. Classically, there is no way to actually be able to tell if somebody is eavesdropping if you're trying to communicate with somebody on a public channel, but quantum mechanically, you can actually tell that somebody was eavesdropping if they were. And so students can actually be taught these things. And you can see here, pre-test score means after traditional instruction, how students do, and post-test scores mean how did they do after working on these quantum interactive learning tutorial. And you can see that in percentage, student performance after traditional instruction is not as good as after working on these QuILTs. And we have done retention studies on many of these QuILTs, and we find that even after several months, students actually retain these ideas. And by the way, one thing that I wanted to say is that a lot of people who are struggling with these ideas after traditional instruction, they happen to be from underrepresented groups. So I think even in terms of promoting diversity, because if you think about who are the people who are privileged, you can see that the people who struggle could often be those people who came from schools and backgrounds which were not really conducive to actually having sufficient background. And so what I want to say is that these learning tools actually help all students, even the ones who are in the maybe top 1/4. But they particularly, they disproportionately actually bring up the performance of the ones who might otherwise be left behind and may not be able to actually contribute to the science and technology enterprise. So we are also developing these tools that we call peer instruction tools. So I'm not sure if you're familiar with this clicker technology, where you can actually get response from students. You can ask them multiple choice questions during class, have them discuss it with their peers, and then discuss the response to those questions based upon what the students have actually been able to do on their own or not been able to do. So the point is, no matter how big the class is, you can actually get feedback from students on their performance in real time so that you can adjust the pace of your class. And students can learn a lot from each other, and that's why we are trying to actually use these clickers with students, in which students are also talking to each other about the answers to those clicker questions during the class itself. And here I'm just trying to show you students' performance on some test related to infinite square well. This is the score versus the percentage of students. This red thing is showing the class in which the clickers were not used, the peer instruction method was not used, whereas these two classes did use peer instruction. In one case, there was a modified questions, based upon the feedback that we obtained earlier. And this is what I mean. This research that we do on how to improve the teaching and learning of physics and quantum mechanics in particular, this is actually an iterative process. So we keep refining these things based upon the kinds of feedback that we get from students about what has actually helped them and what needs to be improved further. So this is, and I've been working in this area for more than 20 years now. So anyway, so I think I want to actually close by just giving another example. One of the things is that what we have found is that even students in the advanced courses often don't use problem solving as a learning opportunity. Like as an expert, when you make a mistake, you often say, why did I make this mistake? What did I need to do, and how did I not think about it? So there must be something about my knowledge that didn't really actually get triggered correctly in this situation, and then I'll learn from this mistake so that I don't make that mistake again in the future. It turns out that many students, even in advanced courses, don't necessarily learn from their mistakes. So one of the studies that we did here that I wanted to tell you about, and let me just go to this particular data here. This study was carried out over a 4-year period in which we gave to students some questions from their midterm exams into their final exam. And when students were actually given the midterm exam back, they were also given the solutions to their midterm exam, in order for them to actually check what they had done wrong. Okay? On the other hand, in 2 of these classes, basically, before the students were given the solution to those exams, they were actually asked to correct their mistakes on their own at home. They were given a couple of days, and they were told, can you correct your mistakes on your own by looking at your books and notes and other things? And what we found, here you can see that the comparison, and they were given some grade incentive. You'll get certain % of your grade back if you actually correct and gave your solutions back, before we give you the solutions. What do you expect? What you find is that there is a huge difference in the performance of students in the comparison group, in which there was no such incentive to correct mistakes before they were given the correct solution. So all students had the correct solution before their final exam, and I'm showing you post means the final exam performance, pre means the midterm exam performance, and you can see that this comparison group where the students didn't correct their mistake, there isn't that much difference between the student performance on the midterm exam and the final exam on the same questions. On the other hand, here the group that was given incentives to correct the mistake, there is a huge increase from the midterm exam average to the final exam average. That's what you're seeing, and in fact you can see the averages. You can see that here the averages are not that different, and here there is a huge difference. So basically one of the things that I'm trying to then emphasize here is that students need to be given incentives to learn from their mistakes, because this is not a skill that they know. They already have learned. And so this study is showing is that even in advanced courses, those kinds of things can help students significantly. So anyway, so in summary, quantum mechanics is challenging, and we are developing learning tools to help students develop a robust understanding of quantum mechanics, so that they can fully participate in the scientific workforce. Thank you. I'll take any questions.